Fridays, we'll YouTube Fridays. Well, the Bills just really took it to the Rams last night. Oh my God. That's as low as I can get it.
You can get a sheet like.
All right. So YouTube Fridays. So I usually, like I said, I just like to look at stuff that's kind of relative to what we've been doing, right? This one I thought was pretty interesting. I saw this last year, just kind of like a visual representation about how gravity works. And I don't know, maybe you've seen this before, maybe high school physics or something. I like it though, because I'd never really thought of gravity being this way. So instead of like, you always wonder about like, well, at least I do, like, what is pulling us towards the Earth, right? Or what is the Earth doing to the Moon, right? Do they have some sort of physical connection? They don't, right? But there is this invisible thing called gravity that's attracting these two objects. And then there's a bunch of videos out there that kind of demonstrates with this. So he just gets a big piece of, I believe, like Lycra, and then kind of lays it out, and that's kind of like space-time. And then you put a mass in the middle of it, and that represents, like a mass, and then that's going to warp space-time, and then which causes things to kind of want to roll in towards it. So I thought this was kind of a cool way. He does all sorts of demonstrations.
You buy the sale stuff, so you don't care what it looks like, right?
Yeah.
For like $20 space-time, they feel that and they're attracted to it.
And they kind of
and so you put matter
that guy in
and
there.
It warps space-time. And so if I have another object, it also warps space-time. They feel that and they're attracted to each other. And so that's Einstein's picture of gravity. Objects warp space-time, feel that curvature, and move accordingly.
Uh-oh.
I'm Dr. Jeff
really?
Binnicker, and today we're going to explore patterns of motion and friction.
Does anybody pay for YouTube? Like, is it worth it? That's what I want to know. Like, you are a person?
No, I know it.
Do they like it?
I guess.
I kind of want to do it because of these freaking ads.
Don't get it. Nobody gets in,
Then they'll get rid of it. Yeah. See, the university, I'll get the university to pay for it. See, like, it's not my money that's doing it. So
Bend space-time more.
you put a bigger mass, right,
Objects
and it bends it more. And then I think what's kind of neat about this too is it kind of shows how like gravity gets bigger as you get closer. It shows you that gravity is not constant, right? Like when we're like on Earth down here, sure, it's okay to assume that it's constant, but as you move away from it, the gravity gets less. I think that kind of, you could really see like I think they call that the gravity well.
respond to that, right? And so you put something there, now it's attracted. Now, in reality,
demonstrate
that
orbits
big
here,
mass
too.
would feel the warping of space-time by the marble too, right? It would move a little bit, but we usually ignore that. The Earth make account. Now it's losing energy, which wouldn't happen.
It's kind of showing how something
in-
goes into orbit. That's what's
solar
happening. Is they
system,
kind of
right?
circle
Not
around it.
noticeably.
They don't ever actually
There's
fall
some
towards it.
perturbations from other
In this
planets
case, it
and
goes
things,
towards it
but this
because
one does lose
there's
energy,
friction and
it's
it's
in.
slowing down. But out in
If I
space,
don't
there's that
push it
friction.
as
So
hard,
keep orbiting. Like
it
our moon
will
keeps
do an
orbiting
ellipse
around it.
for a while anyway.
There's one other demonstration he shows that's pretty cool.
Over here. So one of the things I thought of to do with this is when you study the solar system,
What is he
all the
doing?
planets are going around the sun.
What he's saying there is that, and I actually just this year learned this, that all of our planets in our solar system are all going in the same direction, except for one. Are you aware of this? That they're all going. The other thing that they're all in the same plane, which is also weird to me, right? Like, because what's saying it has to all be in the same plane, right? We're kind of like, our planets are kind of like a ring on it. I don't know how it happened. I'd need to study that a little bit more, but that blows my mind. And they're all going in the same direction in the same plane, right? There's really something we're going this way. There's something could go that way, but nothing's going that direction. So that's just the way the planet was formed. I think the sun was formed. It was kind of spinning a certain way, and everything was kind of going the same direction.
Like a cloud that they all condensed out of?
I think
Clouds
so.
Going the same way, they'd all be going the same way?
Yes, but one's going a different way. But anyways, so he demonstrates it with this. He says like, look, if you have a bunch of particles, basically saying the other ones kind of hit each other and kind of like weed its way out, and whatever was there, he'll see.
Same way. Why is that? Did God decide that he only liked different directions? But there was a preferred direction. The disc it formed from had a slight preference one way versus another, and things going the opposite way got eliminated, and when it's all said and done, everything's
I
going
thought that
the
was
same way.
interesting. And he does it a couple of
That
times and
usually
demonstrates it.
90% of the time.
Is it like a toilet flushing?
That's not like a toilet flushing. Okay. That's an interesting one. I wanted to show that one. And then one other one. So I mentioned too that we did that one problem that had like water breaks. And here's an example of this guy. Which one is the best one? It always comes up sometimes, how many G's can the human body sustain?
The fastest man on Earth scorches down a metal track aboard a spectacular rocket sled at Holloman Air Force Base, New Mexico, in the first of a series of tests of pilot safety equipment. The speed of 421 miles an hour attained by Lieutenant Colonel John Stapp may be doubled before these tests are...
I mean, aren't sensors great? Like now we just put sensors on it. Back in the 50s, they just put a person on there, right? They put this guy on there, right? Got him going 421 miles an hour, and then he hit those like little pools of water. He's going backwards on it, and so when he hits that 421, he's decelerating. And I think they say
But it's
83
already the
Gs.
fastest ever traveled by man in any ground vehicle. The sled is powered by rockets delivering over 50... A new ordeal as science carries man farther into the unknown realm of the jet age.
They don't stress how much. I mean, one of these says it was 83 Gs, and one of them said 40 some Gs. So for a sustained amount of time, for a short period of time, we could take quite a bit. There's all sorts of, you could YouTube all sorts of rocket sleds, Gs, right? There's broken blood vessels in eyes and stuff like that. So just a little side note. Okay, that was our first YouTube Friday. They become more applicable later. I think that's just a cool representation of it. Sometimes I like to have YouTube Fridays be stuff that you could bring up at parties on Friday night. You're just like, hey, guess what, right? There's this one with a slinky later. Awesome. You could use that at a party, yeah.
On the gravity example, the larger objects create a bigger warp. Is that more like thinking that there's like a linear proportion in mass? Is that
We'll look at the actual equation for that in a bit, but there's a gravitational equation, and it does increase with mass, and it decreases with distance. It's inversely proportional to distance. So that equation is G something something over distance squared, I think is what it is. So it absolutely is. The more massive something is, the more gravitational pull it has. Yeah. The other thing that's weird about gravity too is that it travels in waves. Like that blows my mind, right? There's gravitational waves. Like it's not just like constantly pulling. It actually goes. So if right now, right this instant, if the sun disappeared right now, how long would it be till we knew that happened? 8 minutes, right? So 8 minutes we wouldn't know until it went dark. So it would go dark in 8 minutes, and then we would also shoot off on a tangent like immediately, right? And but as soon if it disappeared, we wouldn't shoot off on a tangent instantaneously. It would take 8 minutes for those gravitational waves or the lack thereof gravitational waves to get to us, and then we would shoot off on a tangent. That I don't get. I don't know. That one blows my mind. Okay. All right, so we're right in the middle of this derivation. We were doing normal tangent coordinate system, right? Or sometimes it's called the path coordinate system. This is slightly different than what we did before. There is no fixed coordinate system off to the side. This one has, our coordinate system is actually attached to the particle and moving as it goes along, right? And so what we demonstrated here, it's pointed back that way. So you have one coordinate that's tangent to the path and one coordinate that's normal to the path, hence the name. right? And a short minute later, or short second later, right? My tangent's going that way and my normal's going this way. And then after, a little bit more time, tangent's going that way and normal's going that way. So it can actually flip which direction it's going. And so we defined what those things are, right? These things are great for like describing like forces and things like that in the particle. They're not very good about pointing to exactly where that particle is, right? Because our coordinates are moving as we're going along. So how do we say like where exactly that particle is? But we kind of don't care, right? What we're after is just the forces and stresses and things like that within that particle. And so this coordinate system works, right? We'll talk about converting between the two in a minute here. But so we went through that. We defined our position. Then we talked about our velocity. The velocity is always going to be in the tangent direction, right? I mean, obviously the actual direction that it's traveling is changing, but just the way that our coordinate system is defined, our coordinate system is our tangent's always pointed tangent to the path, and so our velocity is always in the ET direction. ET's changing. But in terms of velocity, it's always in the ET direction. So that's the first part. Velocity is just ds dt in the ET direction, and then ds is just the distance along the path. So how's the basically it's the speed of it. It's the speed of the object as we're going along. Okay, the acceleration, right? We do the same thing. We take the derivative of the velocity. That's what we did. Took the derivative of the velocity, but then now we have this. Taking the derivative of ET. ET changes, so the derivative of ET is not 0. It was 0 in the Cartesian course, now it's not 0. And so then now it actually becomes something, it becomes omega in the EN direction. And so what we get is for acceleration, we have two components. We have an acceleration in the ET direction. That is the change in velocity. That's like stepping on the gas in your car. Right? We're gonna do an example like that in a minute. You're stepping on the gas in the car and you're accelerating along the path. This one right here is the change of direction. There is acceleration associated with change of direction. Velocity is a vector. If you change direction, there has to be acceleration, right? And so this is kind of a version you haven't really seen before, but that's the centripetal acceleration. It's the change in velocity, okay? We're gonna write it in a couple different forms here, right? There are other forms of theta dot or omega. I'm gonna look at this theta dot right there. Can we write that in a different form? The answer is yes, we can. Right? So what it has to do with is like these arc length. It's all based off of this over here. So if we've got this path right here, and this is d theta, and then this right here would be ds, right? The distance between here and here is ds. And this right here is rho, right? That's the radius of curvature, right? We talked about that before. That En points back to the instantaneous center curvature. There is some sort of curvature that's associated with that. And so I can relate these things right here, just using basic geometry, and say that, what am I going to say? I'm going to say that ds is equal to rho times d theta. Right? And all that's saying, right, where I got that from, this is just basic geometry, that arc length is equal to radius times angle. That's high school geometry right there. Right, and then I guess the easiest example is calculating the circumference of a circle, 2 pi times r, right? R is the radius, 2 pi is the angle, and then that's the total distance around is that, right? And so if you wanted to do half the circle, you would just do, the angle would be pi, you multiply pi by the radius, gives you that. And so that works for everything, even quarters and whatever, it comes down to that. So really, that is just, that's supposed to be an equal there. Arc length is equal to radius times the angle. We're going to use this multiple times, so I'm kind of making a big deal about this, right? When we talk about a wheel rolling, we're going to use the same equation, but ds is just rho times d theta. Okay, so let me come back over here, and we say what the velocity is. Velocity is equal to ds dt. ds, we just said, can be written as rho times d theta dt, which is equal to rho times theta dot, which is equal to rho times omega, right? Just kind of interchanging theta dot and omega. So that velocity could be written as rho times omega. And then omega, you can kind of rearrange this and say, well, omega is equal to theta dot, which is equal to v over rho. And I'll write one more time, just gonna make it, or v is equal to rho times omega. So we could take those, I could take these and substitute them up in here. Oh, I can't go between pages, but I can go up here, up into there. So I could substitute omega in for that theta dot there and v over rho, or I can, for the v, I could take the rho times omega and put it up there. Okay, and put everything in terms of v or put everything in terms of omega. And that's what we do. You can substitute it in, then we're kind of done there. So this is how you calculate velocity in this coordinate system. Right, we already said, we just kind of reviewed that. ds, dt, and the et, that's velocity. And then acceleration, the book takes it a step further and kind of defines these things called at and et. You're going to have an acceleration component in the et direction and an acceleration component in the en direction. Just try to clean it up a little bit. The at is just v dot. And then this is the an component. It's either v times theta dot, but that one's not that usable because you have to know what the velocity is and omega. But a cleaner one would be to do v squared over rho, right? Or rho omega squared. I'll highlight those in red or green here. You'll probably do one of these. Right. There you should recognize it. When you've dealt with centripetal acceleration, I think you've done r omega squared or v squared over rho, one of those two. You could use either one of them. Which one is best to use? Well, it just depends on what type of problem you're dealing with. If you're gonna do a problem where you know v, we'll just use v squared over rho, right? If you're doing a problem where you know omega but not v, well then use rho omega squared, right? You can just interchange it back and forth. Okay. Any questions about that? Yes. The omega is, that's a good question. Omega is a velocity, right? It's just your angular velocity. It's how is theta changing with time. The whole thing is the centripetal acceleration. Rho omega squared, that's your, or v squared over rho, that's your total acceleration. So it's a velocity squared times a radius is what it ends up being. Yep. Or a velocity squared divided by the radius. Okay. All right. Special case is a circle. In fact, I think most of our problems when we do normal tangent coordinates, we simplify it down to a circle. Okay. In this special case with the circle, you have a fixed radius, right? Our coordinates here, you would have, let's say if it was traveling this way, you would have ET would be going this way, and EN would be pointing back to the instantaneous center of curvature, like that. In this particular case, we have a fixed rho. Right? Rho doesn't have to be fixed, but it is fixed for a circle. We say that rho is equal to r, that's a fixed radius. S, we can calculate the distance along the path is just going to be r times theta. Right? That's just the arc length times the angle in radians. Take the velocity, that's just ds dt in the et direction, which is ds is just going to be d r theta dt. We carry that out, that's just r theta dot is equal to r omega. So the velocity is just going to be r times omega. And then that's in the et direction, always. The at, the tangential component of the acceleration, is dv dt, which is derivative of r omega dt. Just ends up being r, it's constant, so it comes out of that derivative there. And so this just becomes r omega dot. which is equal to R alpha. That's just the AT component. And then AN is the last thing we have to talk about. AN, that's the normal component. It's V squared over R or R omega squared. You could use either one of those. Okay. And then that's what I've got down here. These are just cleaner written versions of that equation. It's kind of nice. So you can define the whole velocity acceleration. It's just r times alpha into et plus v squared over r. Again, r alpha is a component that's associated with the change in acceleration along the path, and this is the change in direction. And you can do r omega squared or v squared over r, either one of those. All righty. Almost there to do an example problem, okay? So one last step that you may need to use at some point, like I said before, this coordinate system is great about defining like what kind of accelerations the particle is feeling and what kind of velocities, but it's not really good about indicating exactly where it is and its position relative to something else. And so sometimes you want to go back and forth. Oh, sometime in the next couple of days we'll do one where we have to go back and forth between the Cartesian and normal tangent. Right, but you can convert between the two coordinate systems, okay? And it's all based off of this. This is my path, right? And then my coordinates on that path, I've got an ET going like this. And then I've got an EN going like this. Right? And then my Cartesian coordinates I already have on there. These are my Cartesian coordinates, right? Just they're normal to each other, perpendicular to each other. You can see that they don't line up. ET and EN don't line up. But you just simply use basic geometry, and we can look at these two different triangles. Like we can convert the ET to Cartesian with this little guy right here. And then there's this triangle here. So you basically just figure out the different components in both of those directions. This right here is theta. This angle here is theta. And I'll just give you I mean, it's like I said, simple geometry here, but we can say ET hat is equal to cosine theta in the I plus sine theta in the j. And then En hat is equal to negative sine theta in the I plus cosine theta in the j. Right. You can see where that came from, right? If I'm trying to get, right, ET, that's a unit vector. So I try to figure out what that is. I take the cosine theta in the I direction. That's this right here. And then for the j direction, it's sine theta in the j direction. Right? So it's pretty straightforward where that came from. So how you use this, again, we'll do an example a little bit later, but basically, if you do it in normal tangent coordinates, you basically get to a point, everywhere that you see an ET hat, you plug this in. Everywhere that you see an EN hat, you plug this in. And when you do that, it just converts it to the Cartesian coordinate system. Right? And again, you need to do that if you really need to define exactly where a particle is and how it relates to something else. And we'll do that when we deal with relative velocities and relative accelerations. All right. That's all I had there. Okay, let's do an example. All right. Car travels along a circular path with a radius of 300 meters. Speed is increased uniformly from 15 to 27 meters per second in 3 seconds. Find the magnitude of acceleration at velocity equal to 20 meters per second. Okay, 300 meters. So it's this thing, cars just traveling around in a circle. Okay, and then we're asked to find the magnitude of acceleration. right? So the magnitude, that's a little hint that it's not just the vector. We want the magnitude of the vector, but we're gonna get to that. So we can just dive right in and start talking about what the acceleration is. Acceleration, again, you just look back, AT in the ET direction plus AN in the EN direction. AT is the change in velocity over time, and they give us the component to get the average. Does it say constant? Does it say uniformly, increased uniformly? So it's a constant acceleration. So we can calculate AT is just the change in velocity divided by time. So it goes from 15 to 27. So it's 27 minus 15. That's how its velocity changed, and it took it 3 seconds. Right? If it was not increasing uniformly, you would call this the average acceleration. In this case, it says it's increasing uniformly, so this is the actual constant acceleration over that amount of time. If you calculate that, this ends up being 4 meters per second squared. So that is what AT is. Right? It's just the change in speed. The change in speed over time. That's all AT is. It's like stepping on the gas as you're going around that corner. Okay? The AN component is equal to R omega squared or V squared over R. You can do either one of those, right? In this particular case, it wants us to find the magnitude of the acceleration when the velocity is equal to 20 meters per second, right? So in this case, the V squared over R is going to work better, right? Because I was given the velocity. Could you use R omega squared? You bet. You would just have to turn that velocity, you would have to divide that by R, and then that would give you omega, and then you take that omega and then square it and multiply it. You could do either way, okay? Might as well just grab that one, right? So this just ends up being 20 squared divided by R, which was 300. This ends up being 1.33 meters per second squared. Right? So my acceleration vector, we have all the components for it. Acceleration vector just ends up being equal to 4 in the ET direction plus 1.33 in the EN direction. And that's meters per second squared. So that is our acceleration vector. Right? And you treat these things, as like, when we wrote I's and J's, you treat them exactly the same way, right? They're just the base vector that you're multiplying from. So you just write, instead of writing I's, J's, and K's, you write ET's and EN's, okay? So this is where, like, maybe putting in the vector, somebody's talking about putting it in vector form. Like, putting it in vector form here gets a little weird, but you got to think about, like, if I put it in vector form, the first one is ET and the second one is EN as opposed to I and J. So sometimes it's a little bit nicer to put it like this. Right? And then so it asks for the magnitude. How do you get the magnitude of that vector? Just like any other vector, I's, J's, and K's. How do you get that? Yeah, square root of the sum of the squares, right? You often write that with like bars on the side of it. The square root of 4 squared plus 1.33 squared. So you ends up being 4.22 meters per second squared. So that is the actual answer for that one. Any questions? That's a pretty easy one there. Right, trying to do that in Cartesian coordinates, more difficult, right? More difficult, right? Because, like, we didn't talk about centripetal acceleration. You'd have to define, like, how is that, like, it would be complicated to try to do that in Cartesian coordinates. So, hence, doing it in this normal tangent is the same. We're going to see in a little bit, the next thing we're going to cover is, and we're going to do one more example here, but the next thing we're going to cover is polar coordinates. If something's traveling in a circle, I'm going to hammer this home. If something's traveling in a circle, they're almost identical, polar coordinates and normal tangent coordinates. This is because there's a lot, that question comes up a lot. The one difference is, we'll get into this a little bit later, but in polar coordinates, we're going to have a coordinate coming out this direction, and then in normal tangent, one of our coordinates pointed back to the middle. So there'll be a sign difference. That's the only thing that's going to be different. One's pointed back to the middle, one's pointed out. One's going to be negative, one's going to be positive, but they're going to be almost identical. And you could use either one, normal tangent or polar coordinates. Okay, let's do, I don't want to do that one. Let's do this one. We might go back to the other one if we have time. This one, what this one ends up being, this is like that one where I said sometimes they kind of go backwards. They'll give you the position, and then you go backwards and figure out what the velocity and acceleration are. That's this one. They give us the position vector. Theta is a position vector, right? It's traveling in a circle, so you know the radius and what theta is. So you know the position. You take the derivative of this, gives you the velocity. Take the second derivative of it, gives you the acceleration. So that's what this one's about, and it's a little less exciting. This one's a little bit more involved, and we have 20 minutes, so let's do this one. Okay, so this guy, particle A, is traveling around this track. It's going straight, okay, until it goes 200 meters, and then it goes around that corner, okay, which is a circle. It's a circle at the end there, and it travels around that corner to B. And then what we're asked to find is the velocity and acceleration at point B. And this is not a constant acceleration problem. This is an acceleration of function of time problem. So this is where we're going to, tap into our 1D stuff, because it is kind of just a 1D problem down to here, and then it goes around that corner. Okay, there's multiple 1D problems. Okay, velocity acceleration at that point. Okay, so we'll start out with velocity, right? Because we know we're given the acceleration, and we'll get to the velocity. Let me see here. All right, let's kind of lay out, just review what we're going to be doing here first. The velocity is v in the ET direction is equal to ds dt in the ET direction. Acceleration is equal to at in the ET direction plus an in the en direction is equal to v dot in the ET direction plus v squared over r in the en direction. Just kind of just laying out the equations that we're going to be using just to kind of refresh our memories here. This is one of those cases where it's a little weird, right? ET is going to be pointed like this all the way along this path, and then when it gets here, then ET is doing this, right? It's kind of going around. It's going around that corner, so ET is changing. But in terms of that velocity, is increasing. It doesn't care that velocity. It doesn't care that it's going around a corner, right? The person is stepping on the gas. It's accelerating 1 plus 0.2 t, and it's going. It's just, even though it's turning that corner, it's still just accelerating along that path with that acceleration and that velocity, okay, as it goes around that corner. So this thing, I mean, really, in terms of the ET direction, you just think of that thing as just keeping going. You don't have to worry about the turning part. The turning part comes in with this part, the v squared over r, right? So sometimes it's easy to think that way, as I just take this and then I fold it down straight, right? And so it's just like the ET stuff is just continuing straight on that. Okay, anyways, that's just me thinking about it. Okay, let's go back to this. Right, we got to go from accelerations to velocities to positions, and we figure out times. So there's a lot of steps involved here. So we'll start with AT. That's what they give us. AT is what they've given us. AT is a function of time. It's 1 plus 0.2 t. That's equal to dv dt. Right? That's the acceleration equation that they gave us. 1 plus 0.2 t. I take the dt, and I put it on the other side, and say a of t dt is equal to dv, right? That's all I'm doing. I'll do this again. We'll plug in the actual values. Then we integrate this guy and we integrate this guy. That's how we're solving this. So plug in the actual equations. This guy's going for 1 plus 0.2 t dt is equal to dv. This one's going from 0 to t. I don't know that time on the top, but it is starting out at 0 time, and it's going from 0 to v. Okay. Now carry out that integral. This just becomes t plus 0.1 t squared. Right, so just t squared over 2 is what it was. That is equal to v. Okay, and so what that is, right, that's just your velocity equation as a function of time. T plus 0.1 t squared, right? That's just this integral right here is all I've done, right? How do I do that? I'm pretty sure I put it in my calculator years ago, right? You guys learning how to use your calculators? Do it. I'm serious. Do it. Learn it. Learn it. Never once has anybody ever come back to me and said, I really wish I wouldn't have learned how to use my calculator better. Years and years of people coming back and telling me, thank you so much for teaching me how to use my calculator. I don't actually teaching you, I'm just telling you to do it, right? But there's YouTube is filled with all sorts of like help on that as well. Did you have a question?
Yeah, I was exactly where to find out.
Yeah, YouTube it. Yeah. Yeah, there's all sorts of nerds out there making videos about how to use calculators, right? But thankfully they're doing it, right? I mean, but I guarantee if you Googled how to solve multiple equations and multiple unknowns on a TI-89, somebody has recorded themselves doing this. I keep saying I'm going to do it, but how many using TI-89s in here? That's how many A's we're going to get then, I guess, right? And then the rest of you are 84s, TI-84s. Who have many TI-84s? Lots of TI-84s. I think it's because of high school. Is it because of high school? Right, high school. I just talked to my son. He just started geometry yesterday, or this week. And I talked to their teacher about calculators yesterday. And she was recommending the TI-84 because the ACT and SATs allow the TI-84, but they do not. I threw out the TI-89. She goes, no, I wouldn't recommend that. And I was like, well, I do. TI-89 is my baby. And then she's like, well, they don't allow that on the ACTs and SATs. And so I was like, okay, I can see why you wouldn't do that. But it's time. Ask for it for Christmas. Everybody asks for a TI-89 for Christmas. Who's gone from an 84 to an 89? Was it the best decision of your life? of your life. We got 2 yeses.
I had a professor that made us get them.
Oh, really?
In high school, yeah, he was a physics professor, and he spent the first 2 weeks of class just teaching us how to use it.
No, I do have an idea. That's right. I do. I didn't know you could do that. I didn't know you could require 89s. Yeah. It isn't enough. Your life would be so much better. It would. I promise you. I really do. I promise you. You know what? You know what's really weird is I'm up here lecturing to you. I don't know a single one of your guys' names. Not a single one. Not a single person's name. Not a single one. Listen, even my advice, like you're my advisee. I don't know. I know my friend dated your mom, but I don't know. I don't know your name. I know you're from Scobie, right? Yeah, you're from Scobie, Montana, but I don't know your name. Your name is Devin. Hells yeah, I know somebody's name. Okay, I know Devin's name. Good for you, Devin. If I ever have a question, I'm calling on you. Good. I got it. Okay. So that's my velocity equation. Now that I have my velocity equation, I need to relate it to position. I know how far it's traveled in that much time, right? I know that it's gone 200 meters and then halfway around that half circle, right? A quarter way around that circle. So then I can figure out the time and then I can come back and get the velocity. I need to know the velocity at that point because it's going to show up in my acceleration equation. So what do you think the next step is, Devin? That's good. This is good. You go. So then I then look at what. When I go to position, the velocity is just the position, the derivative of position. So I go. This is equal to. this is equal to ds dt, right? And so this is how I'm going to relate it to position. So then I put the dt on the other side, so t plus 0.1 t squared dt is equal to ds, right? And then I kind of knock the dt's or knock the ds's off of it by doing this. This is going from 0 to t. I don't know what that is. This is going from 0 to, I know this, right, to SF, to the final. Right? We haven't talked about what that is yet, but I do know that thing. And then I can calculate what that t is. And once I get that t, then I can come back and put in the equation. Okay, so then if I carry out that integral right there, this just ends up being t squared over 2 plus 0.1 t cubed over 3. That's equal to, we'll call it s of t. Okay, and then I need to figure out what that s final is. S final is going to be A to B, the distance from A to B, right? And so we can figure that out. That's going to be equal to 200, right? That's that straightaway, right? 200 along that, and then this little guy right there, right? That little component, which is an arc length. I know the radius is 50. I multiply it by the angle that's right there, and it'll tell me what that distance is. What is that, pi over 2 plus pi over 2 times 50. Right? And so just to make note, all I'm doing there is the arc length. Remember I told you we're going to do this a lot? We're going to use this a lot. Okay, theta times r. Theta times r. 50 is the radius. Right? So the total ends up being 278.5. Okay? So what I do now is I take 278.5 is equal to t squared over 2 plus 0.1 t cubed over 3. Okay, and then there I solve for t. I'm running out of room here. T. How would I do that? How would you solve that? That's a freaking cubic. That's a cubic. You don't have an equation for that, do you? Do you? Is there one? There's a quadratic equation. It's a cubic equation. Is there a cubic equation? Do you have that memorized? Damn right you don't. How's your? Could you do that on your calculator?
Yes.
Yeah, you have to graph it.
You graph it, you find the zero.
Oh,
And then you find where the intersection is.
pshaw, like you don't want to do that.
Set it equal to zero and graph
What a
it.
loser.
You don't have to graph it.
What are these losers plotting stuff and tracing things?
Also,
The-
you can program this calculator. It's pretty fancy.
Yeah, the TI-89 just said beep, 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 right? Just boop, just out pops it pretty. Oh, even that, and then what's that, Inspire? The Inspire. It's in color. It's in color. It's just. I need to learn. I should get one of those. I might be down. All right, T is 16.33. Think how much time you're going to be wasting plotting stuff on the exam. You know what I'm going to do? I'm going to put a cubic on the exam. I'm going to put you can only get an A if you have a TI-89. I'm going to find something the 89 can do that the 84 can't. Okay, I won't do that. I won't do that. Okay, so then I need to know, the whole point of doing that, right, is I need to know what the velocity is when it goes around that corner. The reason I need to know that velocity as it goes around that corner is because of this, right? V squared over r. I need that for the acceleration. I need to know what V squared over r is at that particular moment, right? So the whole reason of going through that and doing that integration was to figure out what the velocity is at that point. The velocity at t equals 16.33 seconds. That ends up being the 43 meters per second. Okay? Lots of work to get there, but not too bad. So the velocity, we asked for what the velocity, we also need it because the question asked for what the velocity is at that point as well. So you need both of those things. So then V, come back over here for our parts here. The velocity vector is just V in the ET direction, which is equal to 43 in the ET direction, meters per second. That was one of the things we were asked for. Then the acceleration is equal to AT in the ET direction plus AN in the EN direction. All right, we got all the components here. They give us AT, they give us what the AT equation is, right? And so it's just, you plug in that 16.33 seconds into that equation, and what you get is 4.27 meters per second squared. Right? I just took the 16.33 and plugged it into this, right? 1 plus 0.2t. Right? They gave us the equation, and I know that it took 16.33 seconds, and since I know the 16.33, I just put it into that. And so you get 4.27. So the last part is AN. AN of t equal to 16.33 is just V at t equals 16.33. We kind of calculated that already. Divided by R. And this ends up being equal to, we calculated this before, 43 squared over 50. Which is, you plug that in your calc, 36.98 meters per second squared. Okay, those are all the components. Now you just have to put it in the vector. So then our total vector, 4.27 in the ET direction, plus 36.98 in the EN direction. So quite a bit more accelerations associated with going around the corner than it is just from stepping on the gas, right? Changing that direction, going around that sharp corner is what it is, right? So we have one more thing to do, right? And it's polar coordinates, just slightly different than normal tangent. And there's reasons why you would use that one over this one. But then, so we'll get to that. We're going to cover that for the geometry of particle of motion, and then we're going to start relating this stuff to forces, right? Because that's where things get a little more interesting and actually a little more straightforward in my mind. But right, you would feel this force, right? If you're stepping on the gas, right, you need to accelerate that, so your car would be pushing against you to try to get you to go that fast, right? And so you would feel that as like kind of a push on your back. And then as you go around the corner, right, you want to keep going straight, but your car's turning, and so it's saying you can't go straight, so it's pushing back on you, so you feel that force. And so we're going to figure out what those forces are. These are related to the forces. I mean, they're equal to the forces, right? And so we'll figure out how to solve those types of problems next. And that's where we go into kinetics as opposed. This is kinematics. This is all geometry motion. We'll go into kinetics and start relating it to the forces that you would feel or forces required to get these things. Cool. Break. Maybe bring some Lycra to a party tonight, and you guys can demonstrate how gravity works, right? Like, what's that?